November 3, 1942. Naval Air Station Patuxent River, Maryland. Lieutenant Commander Thomas Blackburn watched through binoculars as the 9th prototype Corsair began its test dive from 18,000 feet. The aircraft, designated F4U, had already killed 2 test pilots in structural failures. Now it was about to either validate 3 years of metallurgical innovation or prove that VA's promises about invincible aluminum were fiction. The Corsair dropped like a stone, its distinctive gull wings folding the air into submission. At 12,000 feet, the airspeed indicator passed 350 miles per hour. At 8,000 feet, 400 miles per hour, the wings should have been tearing off. Every aeronautical engineer at Wright Field had calculated the same conclusion. No aluminum airframe could sustain the torsional loads at that speed in a near-vertical dive. The metal would fatigue, fracture, fail, but the wings held. Blackburn lowered his binoculars. The Corsair pulled out of its dive at 4,000 feet, climbing away clean and intact. Somewhere in the skeletal structure of those wings was an alloy that shouldn't exist. According to 1938 metallurgical theory, an alloy that had required 4 years of development, 17,000 hours of testing, and a complete reimagining of how aluminum crystal structures could be manipulated under heat and pressure. The question wasn't whether the Corsair could dive at speeds that would destroy a Wildcat, a Hellcat, or a Zero. The question was how a metal that weighed less than steel could absorb punishment that shattered every comparable fighter in the Pacific theater. The answer lay not in the aircraft's famous inverted gull wing or its massive Pratt & Whitney engine, but in the molecular architecture of aluminum alloy 24ST, an impossible material that had emerged from laboratories at Alcoa's New Kensington Works in Pennsylvania. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was the aircraft that would eventually shoot down 2,100 Japanese planes, more than any other Allied fighter. But in November 1942, it was still an experiment, still unproven, still suspect. The Navy brass wanted numbers. They wanted proof that VA's claims about structural integrity weren't engineering fantasy. They wanted to understand how an alloy developed for civilian transport aircraft had been transformed into something that could survive combat loads. No peacetime engineer had imagined. The metallurgist who had made it possible, a 34-year-old researcher named Francis Frary at Alcoa, would never fly in a Corsair. He would never receive public recognition for solving the problem that had killed Vort's early test pilots. But every Corsair that dove on a Japanese destroyer, every pilot who pulled 9G forces in a major engagement came on May 13, 1943 during a Japanese bombing raid on shipping in Iron Bottom Sound. 50 Japanese bombers escorted by 30 Zeros approached Guadalcanal at 23,000 feet. VMF-124's Corsairs intercepted at 25,000 feet, diving out of the sun in pairs. Walsh's combat report filed the same evening, described what happened. I made my first pass at approximately 430 miles per hour, indicated air speed, fired a 3-second burst into a Betty bomber, observed strikes on the left engine, continued my dive to 15,000 feet, pulled out, and climbed back to altitude. The wings never showed any stress. I repeated this attack profile 3 more times during the engagement. Total dive time exceeded 90 seconds at speeds I estimate reached 450 miles per hour. The ability to sustain that dive speed to continue accelerating when Wildcats would have torn themselves apart fundamentally changed the tactical equation. Corsair pilots could dive away from any Japanese fighter. They could build separation distance, climb back to altitude, and re-engage entirely on their own terms. The Japanese couldn't follow. Zero fighters attempting to match Corsair dive speeds experienced catastrophic structural failures. Japanese pilot Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with 64 confirmed victories, later described encountering Corsairs in his memoir published in 1957. The American fighter dove away from my attack at a speed I could not match. When I attempted to follow, my Zero began shaking violently. The controls became heavy. I knew if I continued the wings would separate. I had to let him escape. This happened repeatedly. The Americans could dive away whenever they chose. We could not stop them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The structural advantage wasn't theoretical anymore. It was operational reality. Between February and December 1943, Marine Corsair squadrons in the Solomon Islands compiled a kill ratio of 11.3 to 1 against Japanese aircraft. For every Corsair shot down, 11 Japanese aircraft were destroyed. Much of that advantage came from the ability to control engagement geometry through superior dive performance. What the pilots couldn't see, what they experienced only as confidence in their aircraft's structural integrity, was the molecular-level battle occurring inside the Corsair's wing structure during every high-speed dive. The 24ST aluminum was performing exactly as Francis Frary had designed it to perform, but the physics involved were extraordinary. At 450 miles per hour in a near-vertical dive, the aerodynamic pressure on the Corsair's wings exceeded 14 pounds per square in differential between upper and lower surfaces across the wing's total surface area of 314 square feet. This translated to approximately 600,000 pounds of force trying to tear the wings upward off the fuselage. The wing spars constructed from 24ST aluminum extrusions were resisting this. Turning fight and walked away intact, every Marine who landed a shot-up fighter on a carrier deck with wings still attached, owed their survival to decisions Frary had made about crystal grain size and heat treatment protocols in 1937. The story of how an impossible alloy enabled an impossible aircraft begins not with test pilots or combat victories, but with the fundamental problem of making aluminum strong enough to replace steel without becoming too heavy to fly. In 1937, when VA aircraft began designing what would become the Corsair, the specifications seemed contradictory to the point of absurdity. The Navy wanted a carrier-based fighter capable of 400 miles per hour, armed with 650 caliber machine guns, possessing enough range to escort bombers deep into enemy territory, and structurally sound enough to survive dive bombing attacks at terminal velocity. Every requirement conflicted with every other requirement. Speed demanded streamlining and lightweight. Heavy armament added mass. Extended range required more fuel, more weight. Structural integrity for high-speed dives meant reinforcement, which added still more weight. The mathematical relationship between these variables was unforgiving. Add weight to the airframe, lose speed; reduce weight to gain speed, sacrifice structural strength. Every aircraft designer in America understood this equation. Most considered the Navy's specifications impossible. The problem centered on the wings. In a 400 miles per hour dive, the aerodynamic loads on a wing surface exceeded anything carrier aircraft had previously encountered. The air pressure differential between upper and lower wing surfaces at that speed created torsional twisting forces that could literally rotate a wing until its internal structure failed. Conventional aluminum alloys used in 1937 aircraft, primarily alloy 17ST, possessed tensile strength of approximately 38,000 pounds per square inch. That was adequate for aircraft diving at 300 miles per hour. It was catastrophically inadequate for 400 miles per hour. Steel could handle the loads. Steel wings wouldn't twist, wouldn't fatigue, wouldn't fail. But a steel-winged fighter would weigh 7,000 pounds empty. Far too heavy for carrier operations. The aircraft would need a longer takeoff roll than carrier decks could provide. It would sink too quickly if the engine failed during carrier approach. It would stress carrier arresting gear beyond design limits. Steel was strong but unusable. VA's chief engineer, Rex Bissell, understood the dilemma intimately. He had designed the Corsair's distinctive inverted gull wing partly to solve landing gear geometry problems. The wing's angle allowing shorter lighter landing gear while maintaining propeller ground clearance. But the gull wing's configuration created additional structural complications. The wing route where wing met fuselage experienced maximum stress loads during high-speed maneuvers. The bend in the gull wing's geometry concentrated those stresses precisely where the wing structure was already. Cycles, simulating years of carrier operations compressed into months of laboratory testing. They tested at temperature extremes, at humidity extremes, in salt spray chambers that replicated Pacific Ocean corrosion conditions. They deliberately introduced defects, scratches, dents, simulated bullet holes, then tested whether cracks would propagate from those defects under load. The results were extraordinary. 24St aluminum when properly heat-treated possessed fatigue resistance exceeding any aluminum alloy previously tested. The material would bend under extreme loads before breaking, giving visible warning of impending failure. It maintained its strength across temperature ranges from -65 degrees Fahrenheit to +160 degrees. It resisted crack propagation even when damaged. Most critically, it could be formed into the complex shapes Bissell's wing design required, stamped and riveted and assembled using conventional manufacturing techniques. FRA published his findings in 1938 in metallurgical journals that aircraft designers read carefully. VA's materials engineers contacted Alcoa immediately. By March 1938, when VA received the Navy contract to develop the Corsair prototype, 24St aluminum was specified for the wing spar structure, the critical load-bearing members that would determine whether the aircraft lived or died in high-speed dives. The first Corsair prototype designated XF4U flew on May 29, 1940. Test pilot Lyman A. Bullard Jr. took the aircraft to 405 miles per hour in level flight, faster than any American fighter had ever flown. The Navy was ecstatic. VA was vindicated. The Corsair seemed to fulfill every impossible specification. Then the wings started failing. The problems emerged during dive testing at Naval Air Station Anacostia in late 1940. During a test dive from 15,000 feet, the starboard wing of the second prototype began exhibiting visible flutter at 370 miles per hour. Flutter, the aerodynamic phenomenon where control surfaces or wing panels oscillate rapidly in air flow, could destroy an aircraft in seconds. The test pilot, Lieutenant Roger Hedrick, immediately reduced speed and leveled off. Post-flight inspection revealed stress cracks propagating from rivet holes in the wing's lower skin panels. VA's engineers were stunned. The wing structure was built from 24St aluminum exactly as FRA's specifications required. The heat treatment protocols had been followed meticulously. The riveting procedures matched Boeing standards for the B-17 bomber, the most structurally sound aircraft in American inventory. Yet, the wings were developing cracks after only 43 test flights. The investigation revealed a problem no laboratory test had anticipated. The Corsair's massive 18-foot diameter propeller driven by a 250 horsepower Pratt & Whitney R200-800 engine generated vibration frequencies that resonated precisely with the natural harmonic frequency of the wing's skin panels. At specific air speeds, particularly during high-power dives, the vibration amplitude increased exponent.